Hello everyone. Welcome to the sixth edition of Renew Education. Please, if you're joining in, please kindly mute your mic so we do not have any interference. So welcome once again. Welcome, Meloxy. Welcome, Dr. Charlene. Thank you so much for joining us. Welcome, Rinred. Welcome, Clinton. Oh, Enoch, you're welcome. Mr. Adi will be giving us a presentation on geothermal as well. So you're highly welcome. Welcome, everyone. Welcome, Precious. I'll go ahead to read to introduce our speakers for today, and they would go ahead to make their presentation. But just to give us a little bit background of who is hosting and why this section is important. So I'm Iwe Shalom Chilaro. I'm the founder of Renew Earth Technologies, and Renew Earth Technologies mainly organizes programs and literally curriculums for people at the grassroots level. And this time around, we're doing like a monthly educational webinar. So we've been doing this in January, and today is the June edition. And all of this is on our YouTube channel. We'll be sharing the link to the YouTube channel. So if you want to take another moment to listen in to any sort of energy type, we've covered wind, we've covered solar, we've talked about climate change and all of those interesting topics. So you can go ahead to see that on our YouTube channel. And with that, I'll be welcoming our first guest, Miss Meloxy, and I'm going to read her bio to us all. I'm so excited about the section, and please permit me to welcome Meloxy. Let me tell you a bit about her, and then she goes ahead to take the floor. So Meloxy is an ocean engineer with 12 years of experience in the maritime and offshore industry. For the last 6 years, she has worked for ORPC, a main headquartered developer of energy solutions powered by free-flowing rivers and tides. Originally from an oil-dependent northern coastal community in Alaska, Meloxy is inspired to support communities become energy self-sufficient and transition away from fossil fuels. Meloxy's main role at ORPC is to design structural components and mooring systems for the company's river and tidal power systems, a clean energy alternative to diesel generators. Her work currently focuses on mooring, system design, data gathering, and community research. Her previous experience as a marine warranty surveyor also assists in ensuring projects meet offshore standards and guidelines. Meloxy is a member of the Marine Technology Society and Society of Underwater Technology. She's involved in educational outreach initiatives to help make STEM subjects more accessible to young women and minorities. Please, with a warm round of emojis, let's welcome our first guest, Ms. Meloxy, for our section. Thank you.
Hi, everyone. It's good to be here this morning. Let me get my screen shared. All right, can everyone see my screen right
now? Yeah, it's not yet on the presentation mode.
All right, can you see the presentation now?
Yes, we can.
Okay, thank you. So I'm going to do a brief introduction on marine energy technology, and I'll give you a little bit of background on myself really fast. But first of all, I want to thank you, the organizers, and I want to thank you who have come here this morning or afternoon to view our presentations. A little bit of background about myself, which I just had a great introduction. I am Native Alaskan. I am from a community that was diesel and oil dependent. And I remember the days when we would have to stress out and worry about whether we would be able to even heat our homes because it was not available in our city because we were dependent on it coming in by ship or by airplane. And during the winters, we would end up having issues with ice outs or severe storms that kept either mode of transportation coming in. So we would end up with heating oil shortages. So that is what inspired me to become involved with ORPC and help small communities become self-sufficient. I am a human. I do have hobbies. So I do like going to the beach and drinking coffee and sewing. So there is more to me than just being an engineer. And I like to point that out because there are so many people who think engineers are, we are just one thing, we go at it and we don't have anything other than that focus. So I just wanted to make sure it's known I am a human and you're allowed to ask questions anytime. So a little bit about our company. We were founded 20 years ago, and in that time, we have started subsidiaries in Canada, Ireland, and Chile. Currently, we have 51 employees, half of which were hired within the last 2 years, which is amazing. We convert kinetic energy and waters to clean, predictable sources of electricity. And we also provide microgrid solutions that we utilize for our systems. And our big objective is to develop these clean energy solutions for small and remote communities, as well as increase and create local jobs for the installation and maintenance of equipment. Let me pull out my laser pointer. Give me just a moment. So we'll start from east and go west. Our Optimor test turbine is currently in Italy. It is doing full-scale testing in a tow tank. And this is so that we can find out the power output as well as the torque and other stresses on the system when it's running. Next, we have what we call the single turbine subsystem test, which was installed last summer. It is a quarter scale test of one of our devices that we currently have in development. And we were able to successfully produce power from it. Next, we have a project that we have installed. It is a RivGen in Patagonia. And then in Millinocket, Maine, we have what is called the modular RivGen, which is in testing to see how we can change the orientations of our RivGen product to match what is needed in each environment. We have a single RivGen device that is in Winnipeg, Canada. And then here's where I'm going to be mostly focusing today is we have 2 RivGens in a village in Alaska called Agiagig. And they have our oldest products and have been working with us since the very beginning. I do want to point out here are our levels of inquiry and our installation points. If you want to look, Nigeria is actually at level 3. We are working on proposals and partnerships with different companies and organizations. So they are on the map. So I'm going to give a brief background on marine renewable energy. We do know, most people are aware we have thermal energy, wind energy, wave energy, and tidal energy. And there are, but no matter what, all 3 of them share the same challenges. We have harsh operating environments. If you can imagine storms acting on wind powered devices and wave powered devices, or for in tidal situations.
Whoa, don't start.
Okay. If you imagine a tidal environment, we also have to worry about what depths we're at and how well our device can perform or be installed at certain depths. We also have to worry about how failure in our technology affects the investors and everyone else, because it does scare people off. So we have to prove ourselves every day how we can be reliable and how we are capable of engineering appropriately. So we are a unique source of renewable energy. I like to say that we are almost as reliable as nuclear. So the marine energy has minimal land requirements. The majority of what we require is an area to build and install our devices once it's out on site. The next thing is we are predictable and reliable. If you imagine the tides, we are able to determine when the high and low tide's going to be, what the depths are going to be, et cetera, from them, as well as rivers. We're able to predict the seasonality of them. Marine energy can help diversify energy supply. One of the things that I am encouraging is working together, all these sources, because again, you don't always have wind working or blowing all the time, and you don't have solar, you don't always have sunny days, and the marine energy supplies, an emergency could come up and you're not able to get back on the grid. So it is important for everyone to work together. All right, so I'm going to go into the ORPC specific devices. We have a tidal generator unit that was again installed last summer. This is a quarter scale unit, so we are actually going up to an 80 kilowatt system for the next step. It is an underwater device that produces electricity from tidal currents. Again, like we had a successful test last summer, and we are in development for a full scale system. And then our RivGen power system produces power from sustainable river flow while it rests on the riverbed. And this is what I'm going to be focusing on today, because I believe the rivers are affecting the general community that is on the call today. So we have the longest operating hydrokinetic project in the Americas. We have successfully deployed over 18 consecutive months. And that was actually kind of accidental. It happened because of COVID, and we weren't able to get out to the location it was at. And it didn't require any intervention, and it was able to perform as expected during that entire time. And so far, the important thing is we've seen no negative effects on the environment. This includes wildlife and flow of the rivers. And it's really cool, like this image of the ice, we are able to work with things going overhead. Okay, so marine hydrokinetic benefits. The advantage of river projects. Let me go ahead and describe a capacity factor really fast, because I know most people don't know it. A capacity factor is how much is actually produced. So let's say you have a car and it's going 80 kilometers per hour, but you start considering that, oh, you have to stop at stop signs, traffic isn't always going 80, etc. So during the day, you are reducing your speed, increasing your speed, etc. And by the end of the day, you might see that you've only had 40 kilometers per hour. Now that means that you have a capacity factor of 50%. So I hope that makes sense and explains it a little bit. But you can see that, and these numbers were adjusted for Nigeria specifically. So we have a capacity factor of 65% in Nigeria, and our footprint for that would be only 0.12 kilometers, which is the little blue box here. A wind project has only 8%, and that is this big green box here. And a solar project has 13%, which is our little yellow box. So you can see why we believe and know that hydrokinetic energy is a more reliable source of power. So through these projects, we've demonstrated that the benefits of off-grid or remote community moving to marine renewable-based power can be dramatic. Independent academic research has shown that a RivGen system has the potential to reduce the carbon intensity of a community by 98%, switching from diesel. And this can save a community over 3.4 million liters of diesel over the lifetime of a project. So given the exposure of remote communities to the current upward trend in fuel costs, which is astronomical, solutions like this, have never been more important for us. And so here's a little bit of information about how the way that this works. We have a microgrid, which are marked by our smart controls, or what I like to call our magic box, is in the middle of everything. And it can intake from solar, diesel, or wind on top of our RivGen devices. So what happens is the electricity from the RivGen device goes into our microgrid. And then magic happens and it gets put out onto a community scale baseload power. Or if the need isn't as high and we have excess electricity, it can be sent to an energy storage system, which acts like a giant battery. So when the electricity is needed, again, it can be returned to the microgrid. Should something happen to the RivGens where they need extra power submitted to the microgrid, or even if we're just working in conjunction with these products, we can use solar, diesel, or wind to work as a backup as well. And actually, currently in one of our projects, we have a solar panel that is on our microgrid, excuse me, to give us excess power should anything go out, because we need to keep our excuse me for a second. We need to keep our sensors and everything available for us to be able to read remotely. So the energy potential for a single RivGen, we could power 2 to 6 public buildings at once. We can power 550 to 1,600 homes, or we could send an electric vehicle around the world 50 times. The caveat with the 2 to 6 public buildings is that is based on US public buildings that have refrigerators and other high electrical usage items in it. So it could be higher for remote communities. The 550 to 1,600 homes, the reason why there's such a great variability there is because we don't have enough research to say how the seasonal variability in the flow of the rivers, where this information is taken from. But we still see a benefit of baseload power, minimal land impact, and it coexists with marine life well. So here is information on our target communities and solutions. The immediate need is remote communities, and I'm going to repeat that over and over again, because again, that is my passion. So 2 billion people live in remote communities with no access to traditional energy infrastructure. 700 million have electricity, but rely solely on diesel power generation. 17 African countries, which is this table, have more distributed diesel generation capacity than grid-connected power generation. And if you see, Nigeria actually has the highest amount. Decentralized renewable energy allows countries to skip the poles and wires and have large infrastructure development. And there's also significant economic development and social justice potential from improved access to power. So in our remote communities, specifically Iggy, we can combine with batteries to provide the baseload renewable electricity. We have been able to run with the diesels off 60 to 90% of the time in Iggy. And one of the reasons why we have it could be higher, but the reason why it's not is because they cannot turn off their diesel generators because it takes so long for them to kick back in. So that's where the 90% comes from. The microgrid and energy storage system was developed with Schneider Electric. And I believe that might be a familiar name for some or most people on the call. So we have modular decentralized generation capacity, can be deployed as individual units, which we have done. We have small arrays, which again is our situation in Alaska, and we can do large capacity arrays. So you have a wider river plus a higher need, we will add 3, 4, etc. And it's been proven in challenging environments. It's been through multiple winters, negative 40 degrees Celsius temperatures, and rivers freezing over and the ice running straight over it. The ease of logistics, it can be shipped on standard trucks and containers, assembled, installed, and O&M used local resources and equipment, which is very important. It boosts the economy as well as the pride the community has in the project. So here's some details. Conventional types of river hydropower. We have diversion or runoff hydropower here. Channels flowing from water from a river go through a canal to spin a turbine, and the flow can be regulated by the facility here. So here is what we are, excuse me, I have it in the wrong order. This one is the diversion. The impoundment is a system that uses a dam to store the water, and electricity is the water is released to produce electricity. And a pumped storage hydropower is kind of like a diversion, only it requires the usage of another power source to be able to fully run. And I can describe that more if you'd like later on, but it again works like a giant battery. It stores electricity from other power sources and runs from there. So the way that we differ is that we do not block the flow of the river like dams do. We do not divert the flow of the river. The cross turbine design allows for shallow water deployment, as well as is scalable for different locations and can be installed and removed as necessary. One of the other important things is that we are able to have fishing vessel traffic go over the device because of its depth. So that was majorly important for where we have been installing lately. So the underwater power system can operate in river or tidal environments. It can generate 40 to 80 kilowatts based on the water velocities, and it can be deployed in rivers that are only 5 meters deep. So it's very, very usable in different locations. And then the way it works is you have these 15-meter pontoons that are 14 meters apart that float the device out, and I'll describe their installation in a second. Here is how our shore station, AKA the magic box, works. It starts, we have a 10-foot container over here that everything is stored in. The AC from the on-device generator is sent to the shore station via a power and data cable. The variable frequency drive rectifies the variable AC into stable DC. An inverter converts the DC into grid-ready AC. And then there are onshore device controls. So those are the things that allow us to alter how much needs to go on the grid, where it's being supplied to, etc. Our computer interfaces and networking are also in the container, and our disconnects between the grid and the RivGen are also in there, as well as a transformer. Here's a little bit on the engineering. These are analytical tools that are used by us specifically. There are more available depending on what sort of work you're doing for the marine hydrokinetic industry. We do computational fluid dynamics, which utilizes a program called OpenFOAM. It's open source and it's absolutely great. We have deployment analytics for the design. It utilizes Proteus, which is very simplified modeling. And we do our assemblies drawings in SolidWorks, and our results and checks are utilized using SMath, which is a program that utilizes all of the different units and is able to do all of the computational work that we need. So the project execution, it includes the community, it works with the local resources, and that is where the biggest success of the project lies. So this particular community you can only get into by plane or by going upriver in a barge. And so this is our shipping of the pontoons here. As you can see, it can fit on a 40-foot barge just fine. I don't know why it keeps doing that. It is installed using bucket loaders. And then we have a small tug operated by John Salmon that is used for installation, and all of our welding and everything happens on site by local resources. So the deployment occurs. We have our transportation to site in different manners. We have unload and assembly on the beach or wherever is available. Again, like you can see how minimal the equipment we have available is and how we're able to be successful in that. So while that's being assembled, we'll go ahead and set the anchor in the mooring. And then once that's in place, we can move the device to the water. And then bring it out. So generally, like our extra workspace is a barge. We have extra tools, our power and data cable, etc., on there as we need. And the device is towed out to the location. It has all the attachments made, including the power and data cable, and it is sent to the river bottom by ballasting the pontoons. And then all the connections are made at the shore station, and then it is put onto the grid there. And we've shown again that we can work in even harsh environments. So here's what we have happening for the future work of Nigeria. The initial focus is on river opportunities along the major waterways. We have potential tidal energy opportunities in the Delta region, and a partnership with Contemporary Architecture Limited. ORPC is also members of several global organizations in the industry that is supporting us in Nigeria. So the next steps to advance our projects in Nigeria, we have to have a devolution on the power sector in 2023. The potential work for state governments to build distributed renewable energy capacities to meet their growing electricity needs. Multiple support programs exist to fund the initial pilot projects. And then we have interest in working with local governments, communities, and the private sector to identify and develop sites on fast-flowing rivers. So we do have a couple of universities that are working with us on that last point. The information we need are the velocities of the sites as well as the depth. And we need to see how that varies throughout the year because rivers are seasonal. You have the rainy season, which increases our flow and our depth. And then you have the dry seasons, of course. In Alaska, we have to worry about the runoff during the winter. Once it melts in spring, we ended up with high flow rates and it stays steady throughout the summer. But then, of course, winter, it slows down because everything is frozen. So I'll give a brief description of our TideGen. Again, I didn't think that would affect this particular audience too much, but it is, again, in discussions for the Delta region. This is rated at 80 kilowatt hours and can go up to 190. It is operational up to 3.5 meters per second, at which point we have to cut off. And then we have 16 to 22 meter water depths that we can work in. It's dependent on the depth of vessels. So our current project is 16 meters below the surface because of how large the ships are going over it. The device utilizes a turbine, brake, and generators that work from the RoadGen system. So we have proven that that technology works, and so we're sticking with it. And then that is all I have. But one of the things that I wanted to bring up as well is the environmental impact. We have yet to see any fish deaths, and the environmental footprint is small enough that we have not seen any issues to riverbeds. A couple of other things is the site in Igiage is one of the largest salmon runs in the world. And again, it's a miracle that we haven't had any issues with fish fatalities or disruption in their smolt and salmon run seasons. But that is it on what I could describe for river technology and what my company does in such a short amount of time. I wanted to go more into the Tidal side because that is what I focus on. But this is what I have, and I'm open for any questions.
Oh my, this is great. This is amazing. And I was really wrapped around the technology. Honestly, I would really love for more clarifications on some parts of the demonstration and things like that.
Yeah.
Um,
So are you talking about this page or?
no, I think it was the part where you were showing the demonstration of how it's been launched and installed in the
Yeah,
rivers. Yeah.
like this? Okay. What sort of questions do you have regarding that? It is a very well coordinated process with local resources. So, and
Mhm.
I absolutely love that.
Yeah. I mean, I was just saying this is like a great opportunity, even that the project is coming to Nigeria, that will create a lot of jobs for the local
Mhm.
communities there.
Yes,
Oh,
yes. And then not only that, but you have the influx of our employees or extra
mhm.
resources that we have to bring in. So then you have a more of an economic boost there, not just in the physical work of the project.
Okay. Think we have like 2 minutes, so maybe I would let Rinred say something, ask her question directly. But there are questions in the chat box, and we'll still
Oh,
answer
there
that.
is.
Yeah, like I mean, 3 questions probably. So
Oh,
Rinred,
okay.
go ahead.
Let me. Oh goodness, I wasn't paying attention. The slides, yes, I should be able to. Let me double check with my company about that. Um, let's see, does it generate? No, it does not generate any heat that we've seen. We have all sorts of sensors on there. There are temperature sensors so that we know everything is running correctly and there is no damage to the system. How far away and depth is it installed to the ocean? So I went over the rivers, and it is, I can't remember how wide the river is, but again, based on its depth or excuse me, the width and length of we are able to install multiple in one river. Um,
Mm.
as far as in the ocean, it is preferable that they're in within 1,600 feet from shore due to the power loss in power and data cables. So the tidal devices do not go out that far. The depth varies. Again, it's based on what traffic we have, as well as it can vary on where the best flow is in the water column. Theft and vandalism. We have had issues with theft on a couple of our shore stations. We learned very quickly we need to put up fences, have people, local resources go out and check on it every now and then, things like that. Someone stole a generator from us, which was not fun. We had to close off ladders. We learn each time, that's for sure. And we always hope that people don't get in because that's where it's really dangerous. Something being stolen, yeah, that's terrible, but someone getting injured because of accessing that is catastrophic.
Yeah.
Does it pose any adverse effect to the aquatic life? No. So far we have not seen any issues. We do run acoustic scans or excuse me, we have acoustics on it to check how much noise it's making. And then it's also really important for us during that test we did, the tidal test, because where we are installing does have whales and things like that we are working with. And so far the sound levels are fine for marine mammals and different fish life. The only time we imagine it being a problem is during installation, and that is installation of anchors. And unfortunately, that is due to the technology of that, and we have no control over how that is done. It's kind of one of those things we have to choose, and someone comes out and does it for us. Let's see. What size of the RivGen system? Again, it is 15 by 14. It floats after installation. We can float it as we want. So it sits on the riverbed until we come out. We have a pop-up buoy that we use a release. I can't remember what acoustic release on that allows the pop-up buoy to come up. We tie into that, and we go ahead and fill the tanks with air, which is what allows it to come up to the surface. And that is done from a boat. It doesn't require any shore work. And then the slides, yes, I'm sure I can get you the slides. I just have to ask. And the first deployment of the technology. Ooh, so that's kind of hard to describe. So it's 2024. We started in 2004. I believe in 2008 was the first device that went in the water, but it was not a RivGen. Our first successful RivGen went in 2016, and we've been developing since then. So the RivGens that you see out in Igiagig that I've been describing are not the same ones. The first one is the one we learned from, and then we produced the even better systems. Let's see, first deployment. How do you get into it? Recommending courses. So if you want to go on the engineering side, there are plenty of resources that I can point you in. We also have so many different positions within just our company. We have regulatory people, we have management people, we have research people, we have community relations people. So honestly, you can start anywhere and end up here. Like, I actually studied theater first. And then I found out about ocean engineering and saw how it could impact the communities. And I said, well, I don't need to be in theater, but I want to impact these communities. So let me go for this. So you can always jump over from anywhere and choose what works for you. But yes, if you want to email me about recommended courses, I'm happy to answer those. There's a lot. Are there any other questions?
I would just lead that maybe the questions stay to the end of Charlene's presentation so that we can look at that as well, and then we can discuss if that's fine with you. Would you still be available after Charlene's presentation?
Oh yeah, I'm available.
Oh, thank you so much. Thank you. Great.
You're welcome.
So I mean, that was amazing. I was expecting to see a lot of fire emojis. I was thinking this place will be flooded with like fire emojis, because that was really impressive. I didn't know that Tidal Energy had such amount of like power generation, and this is it's really impressive to see. I hope that Tidal River Energy can really be supported much more and receive such kind of like presence as much as solar. So that was really interesting. Thank you so much, Leslie.
You're
And
welcome.
I'll go ahead to invite our second guest for today, and permit me to tell you a little bit about her, reading her bio, and she's going to take the floor after this. All right. Just a moment, and the bio will be up. All right. Thank you so much, Dr. Charlene, for joining us. Dr. Charlene Smith is a nuclear engineer and scientist at the Electric Power Research Institute. I'm always blown by engineers. Charlene co-leads innovation for EPRI's nuclear sector Dr. Charlie also holds research scientist appointments at the University of Florida, where she acts as a collaborator on nuclear materials research projects. Prior to joining EPRI, Dr. Smith was a distinguished research fellow at the Idaho National Laboratory and a research scientist at the University of Florida. Dr. Smith holds a Bachelor of Science in Mathematics and Chemistry from Coppin State University, as well as a master's degree in nuclear engineering and a PhD in nuclear engineering, both from the University of Florida. Dr. Smith's research expertise is in advanced characterization and post-irradiation examination of nuclear fuels, authoring more than a dozen peer-reviewed manuscripts in the Journal of Nuclear Materials, Journal of Material Science, Nuclear Engineering Design, and Micron. Dr. Smith leads multiple international initiatives, including the Nuclear Energy SMR Symposium and the Nuclear Engineering Bootcamp, aimed at advancing education and research infrastructures in developing countries. In recognition of her academic excellence, Dr. Smith has been honored with the Jamaican Prime Minister National Youth Award in Academics, bestowed by the Most Honorable Andrew Holness, 12th Prime Minister of Jamaica. And with our fire emojis once more, let's make welcome Dr. Smith for our section. Thank you so much for joining.
Thank you so much for having me. So let me go to sharing my screen really quickly. So Melosi, definitely learned a lot from your presentation. And as you were going through, I was thinking, I should start adding tidal wave energy to my slides, because I generally broadly talk about clean energy solutions and how we can, diversify a clean energy grid so that we're looking at we're having energy resilience and energy security. Thank you so much for the kind introduction. Again, I am Charlene Smith, and my presentation is going to be a bit more, it's going to give a bit more background, because typically when I have conversations or gives presentations on nuclear energy, I find that there's a lot of background work that needs to be, background information that needs to be communicated before we really get into the nitty-gritty of things. So just to introduce myself again, I'm Charlene Smith. I was born and raised in St. Catherine, Jamaica, where my experience growing up in Jamaica ultimately led me to making the decision to go into the energy industry, particularly from my experiences with energy unreliability, particularly during extreme weather events like hurricanes, tropical storms, etc. So following graduating from high school, I moved to the United States, where I pursued my bachelor's degrees in chemistry and mathematics. The school that I attended didn't offer engineering, which is what I really wanted to do. And in particular, I wanted to work on solar energy, which I did. But the majors that I, felt made the most sense to combine was mathematics and chemistry. And so that's why I have those degrees. And so because naturally I grew up on an island in the Caribbean, the first energy source I turned to was solar energy for obvious reasons. We have sunshine for most of the year. It just makes sense. But after going through different research projects pertaining to solar, the intermittency and the reliability was a constant point that came up. And so as a part of my work, I wanted to seek out clean, reliable energy sources that could all be mixed together so we can have a good diversified energy structure that is also clean. Because Jamaica primarily uses oil that is imported for electricity. So after achieving or obtaining my bachelor's degrees, I switched from solar energy and got interested in nuclear energy for the reasons I mentioned before. And so I went and pursued my graduate studies, both my master's and PhD in nuclear engineering from the University of Florida. And it just so happens that by the end of it, I was the first Black female to graduate with a PhD in nuclear engineering. That was not something that was planned. well, from the University of Florida. That's not something that was planned, but that just ended up being the case here. And so following my obtaining my PhD, I went to work as an engineer and scientist at the Idaho National Laboratory, which is the leading laboratory for nuclear energy research and engineering in the United States, located in the middle of nowhere, of course. And then after that, I decided to, dip my toes into nuclear policy and regulation on that side, which, by the way, I had no previous academic background in. I just wanted to see what's going on in that area, especially since there was a lot of interest in the US, by the US, to kind of accelerate nuclear energy deployment through advancing regulations and policies. Spent a little time in policy and regulation, didn't love it. So I went back to engineering shortly after, had the opportunity to present my research in multiple different countries. Let me minimize this so it's not in the way. And currently I am at EPRI, the Electric Power Research Institute, as a nuclear engineer and scientist. So I wear both hats. And I'm also a research scientist at the University of Florida, where I primarily collaborate with upcoming PhD students on their research projects. And in my free time, I typically like to go back to Jamaica, develop different educational programs to introduce fields of study that are not currently offered anywhere in Jamaica or in the wider Caribbean. And so one of those disciplines that I really focus on when I go back, typically in the summertime or in the springtime, is to teach high school students, university students, and even professionals and the general public on nuclear engineering concepts. And the reason for that is because the Prime Minister of Jamaica announced interest in exploring nuclear energy, to including their energy grid. And so that I used that opportunity to go ahead and develop some technical programs and have those launched in Jamaica. So jumping right into it, of course, we know that, we use energy for different parts of life, whether in the residential, commercial, transportation, and industrial sector. I think the underlying point here that I'm trying to communicate with this slide is that we need energy. We can't really, get away from it. And so with the need for energy, we have the option to look at a slew we have a bunch of different options that we can choose from, right? And some of these options are listed here. But choosing the different energy sources, right now is critical. Choosing the right ones, at least, is critical because of climate change. And I'm sure you've already had webinars on climate change, right? And that's emphasizing the importance of addressing it. And so energy is a big thing that ties into that. And so when I give these talks, particularly in Jamaica, I like to make the statement that, small island developing nations, right, although they're not on the forefront of contributing to greenhouse gas emissions, they're on the front line to receiving the brunt of the effects of climate change. And so these are different effects that we're seeing all over the world. These are just a few that I've listed here. But typically this comes up because when I talk to folks in Jamaica, they're saying that, well, we don't really need to transition to clean energy because we contribute to less than 1% of global carbon emissions. While that's true, you're still on the front line to receiving those impacts. And so if there are, extreme weather events, small island developing nations are the most susceptible to damages. And why are we talking about energy in the first place, right? We're talking about energy because when we look at the contribution of global greenhouse emissions, energy is a huge contributor, right? Because again, we use energy in the residential sector, the commercial sector, in our hospitals or schools or workplaces, in transportation, and in industrial uses. So trying to minimize or decrease the contribution of global greenhouse emissions from energy here is a top priority, because that is the main driver for climate change. So with that, let's go ahead and talk about all the clean energy sources, right? So because climate change is at the forefront of of what is directing the decisions that we make on deciding what clean energy sources or what energy sources to look at, we want to first and foremost share or consider ones that are clean. So if you look at the rightmost side of this graphic, it's ranking the cleanest energy sources from the least from the most clean at the bottom up to the energy sources that are considered dirtier. And so if you look relatively at this particular graphic, solar, nuclear energy, wind, hydropower, and biomass, they have the lowest, they're some of the cleanest energy sources, right? And so as we're moving forward, we first start with, okay, we need to figure out what options that we have in terms of energy sources that are clean. And then look at the second attribute, which is arguably the next important attribute, is whether or not those energy sources are safe. And so if you look at the left side of this graphic, it's looking at the death rates from both accidents and air pollution. And again, you see solar, nuclear energy, wind, hydropower, and biomass, natural gas, in this case as well, are showing that they are the safest energy sources. When you look at this graphic as a whole, and we're here to talk about nuclear energy. Nuclear energy is considered the safest as well as the cleanest energy source, which surprises a lot of people sometimes because of the stigma around nuclear energy as being something that is unsafe or dangerous. Now, and I think it goes without saying that all energy sources are not void of risk, right? All these energy sources, from solar all the way to coal, they have risks associated with them. However, there are safeguards that can be implemented to be able to minimize that risk. And so even with the inclusion of the accidents from Chernobyl and Fukushima, nuclear energy is still ranked as the second most safe energy source following solar. And I'll discuss in next slides what exactly, what are the engineering features that makes nuclear energy so safe. All right, so moving forward from until the end of the presentation, we're just going to be focusing on the cleaner energy sources, right? And it's important that we have options when we're looking at clean energy sources, because the more diverse your energy grid, the more reliable it is, the more secure it is. So let's talk about Jamaica for a second. Jamaica has set a global renewable energy target to have their grid make up of 50% renewables by 2030. It's now 2024. 6 years from now, Jamaica is attempting to go from about 13% renewables to 50% renewables in 6 years. Very, very, very ambitious. But that's the goal that has been set. Primarily, Jamaica uses oil and natural gas beyond renewables as a part of their entire energy mix. And what's important to note here is that solar energy has huge potential in Jamaica. Why? Because we have sunshine for most of the year, right? And I think that having a strategy that is tailored specifically to the region that you're looking at, in the case of Jamaica, at least it's my view that Jamaica should build out as much solar as we can and use that as the main driving energy source, and then have other clean energy sources more or less act as support or act as batteries to be able to support solar energy when there are times of intermittencies. So this is ultimately what I see the evolution of energy looking like in Jamaica. So we started off with coal, using fossil fuels and hydro, and we're looking on the left side of this table here, non-variable energy sources that are considered baseload, and on the right side, variable energy sources. So in the past, we've used coal. Right now, it's primarily oil and gas and hydro, but our hydro capacity is still very low in comparison. And so right now is ultimately, here is a transition period, if you will, for Jamaica, because they've expressed interest in considering nuclear energy. That means that as they transition to their clean energy goals, they're going to want to remove a lot of their hard or heavy carbon energy sources, particularly oil. And so it's not a case where you say, okay, we want to go 100% clean energy. Let's immediately shut off oil and gas and just see what we have. That's not something that is feasible. You need you need to be able to have a smooth transition, and what that means is that utilizing natural gas ultimately to help with that transition, while we're considering other clean energy sources, including nuclear, and while at the same time we're building out a lot of solar. And this case is specific to Jamaica, right? So you could consider different templates for different regions depending on what type of assets you have from an energy standpoint. And then ultimately, when we are at 100% clean energy economy, once we've developed an infrastructure in the transitioning period for nuclear energy, we have a regulatory body, we have policies that incentivize nuclear energy, and we have the human capacity to be able to get that industry up and running, then we can look at having nuclear energy and hydro supporting primarily solar, because solar has the most potential naturally in the region. So let's talk about nuclear energy. I'm not really sure what the background is for everyone, but I'll try to break it down from the fundamentals, and then we'll work our way up. So nuclear energy is the energy that's released from the splitting of atoms. I don't know if you can see my mouse. Can you see my mouse? It's moving. Just need confirmation if my mouse can be seen. Yes,
I can see it. Mm.
Okay, great. So nuclear energy is energy that's released from the splitting of atoms, right? And that reaction is something that is taking place in the core of the reactor, where you have the fuel, primarily U-235, where we use a neutron to fission the heavy atom to produce two smaller nuclei. And in general, 2.5 neutrons technically, but for the sake of visual demonstration, you see these graphics having 3 neutrons coming out. And so when you have the fuel and there's fission, the fission reaction is occurring in the fuel itself is surrounded by water. It's filled with water in this reactor pressure vessel. And so you can imagine as fission is happening, you're producing energy, you're producing heat. That heat is being used to heat up the water around the core. And in this design, it's a pressurized water reactor design, right? So the function of the pressurizer here is to prevent the water from boiling, right? And so it comes over as steam into the steam generator, right? And so you have the steam generator here that is bringing the steam to the steam line that is turning the turbine, and the turbine is connected to the generator, which then goes to the transmission lines, right? However, so some of the steam, not all of the steam is going to go to the electric generator, right? So you have some that's going to flow down into the condenser, where it's converting the steam back into water and it's plugging it back into the steam generator. And you also have a nearby water source that is pulling water into the reactor to continually cool or control the fission reaction as energy or heat is being produced. And then you have some of the steam that's dissipated into the cooling towers that you see here. So what you see when you see the cooling towers at nuclear plants, it's not greenhouse gas emissions, it's just water. Let's talk about, and so, when I show this graphic and I go through the process of this is how a nuclear reactor works, in this particular demonstration, a pressurized water reactor, is it considered clean based on the explanation that I gave? Yes, I would say it is considered clean. The question is it safe? Like looking at the first attribute, we want it to be clean. Second attribute, is it safe? Let's talk about safety. Now, one of the first things that usually comes up when I talk to folks is the radiation. Okay, let's talk about radiation for a second. Radiation is something that is naturally occurring. It's all around us. In fact, if you look at this graphic, most of the radiation exposure that we receive on Earth comes from background radiation. Almost half of it, right? And the second largest contributor to the radiation that we're exposed to actually comes from the medical field, because you need to produce medical isotopes to detect and treat different types of cancers. You need to perform x-rays. If you've broken a bone, that's you being exposed to radiation. And the part that nuclear power plants fit in is this area here that's occupational. And so in the grand scheme of things, the radiation exposure that you receive from a nuclear power plant, or living near to a nuclear power plant, or even being a employee at a nuclear power plant is less than 0% compared to the rest. So let's put that into more context, right? If you go to the hospital and you get a whole body CAT scan, right? You getting that one CAT scan, you're receiving 1,000 times more radiation than living next to or near a nuclear power plant in 1 year.
Wow.
Just to give you an assessment of what that is, right? Again, if you are living in a high elevation area, let's say Denver, Colorado, Colorado, or Seattle, for example, you're receiving 500 times more radiation from being in that elevated space compared to living near a nuclear power plant, again, for 1 whole year. Same thing, even at the sea level, because if you go down, the lower you are in an elevation, the less radiation you are exposed to. The higher you are in elevation, the more radiation you're exposed to, which kind of, you know, shows when you go and take a cross-continental flight, the exposure that you get from being in the airplane is extremely high because you're at a high elevation. But even if you're at a lower elevation, being on the beach, for example, in Jamaica, I would be exposed to less radiation in a year than if I lived near a power plant. Just to put things in context here. And so let's talk about it. But that doesn't mean that the nuclear power plant does not expose you to radiation, and I'll explain that it does. But then talk about safeguards as to, you know, why does nuclear rank as being the safest as well as the cleanest? And we're going to talk about that in a minute. So the types of radiation here that is considered harmful to you is ionizing radiation. These are different types of ionizing radiation, with the exception of neutrons. But neutrons can induce ionizing radiation. So you have all of these different types of radiation. They're harmful to you because they're ultimately stripping an electron from an atom and ionizing a particle, right? But in all of these cases, so for your alpha particles, it can be stopped by a sheet of paper or your skin, right? Beta particles can be stopped by a thin sheet of aluminum or a piece of wood. Gamma rays can be stopped by lead, and neutrons can be stopped by water. Almost all of them can be stopped by water, right? So if you look at from the types of radiation that travels the shortest distance to the radiation that travels the longest distance, if we were to use water or concrete, easily stops the alpha rays. Water or concrete easily stops the beta rays. Water or concrete definitely stops the gamma rays and X-rays. And the water also slows down or stops the neutrons, right? And so I want you to consider these materials, right? If you are exposed to radiation, if you have alpha source, a beta source, a gamma source, with no protection, you will receive high doses of radiation, especially if it's gamma radiation, right? And these are all different types of radiation that is produced when you're talking about a nuclear fission reaction in the reactor. But let's talk about the design of the nuclear power plant and how that makes it safe, right? So this is kind of an open 3D rendering of a nuclear power plant. I mentioned before how nuclear energy works, or how heat is produced. Here is the reactor pressure vessel that I showed you before, and how the fuel is close to the bottom of that assembly. The fuel, again, it's what? Surrounded by water, okay? Going back to the materials that work effectively to stop radiation, right? Water or concrete, okay? So first of all, the fuel is surrounded by water, right? And that in of itself is radiation protection, the water, right? Moving away from the reactor pressure vessel, we go towards to the internals. We go towards the reactor vessel itself, which is about 4 to 8 inches thick in steel. Then we move out to the bioshield that's 4 feet thick. That's concrete and reinforced steel. We go out even further to the weir wall, which is another 1.5 feet thick concrete. Then we go out to the dry weld wall, which is 5 feet thick, reinforced concrete. We go out further, we have 1.5 thick inch steel. And then to the building wall, it's 3 feet reinforced concrete. And so the design shows you that there are multiple redundant layers of protection, right? And that protection is explicitly because of this diagram here, and us being able to effectively protect ourselves against exposure to radiation, right? Without these redundant systems, you're getting exposed to a lot of radiation, right? But even in these systems, I mean, it's you move out further from the water, you have concrete, then you have more concrete, then you have reinforced steel, then you have more concrete and more concrete and more concrete. Looking back at what's harmful to you with respect to ionizing radiation, it's built into the design of the reactors to protect you from radiation. Not only that, if we look at a study or some experiments that was done at Sandia National Laboratory in 1988, they wanted to test the durability of these reactor containment buildings, right? And so they constructed the same sort of reinforced steel that's used in these nuclear power plants. And they took a F-4 Phantom jet going at the speed of 500 miles per hour, or approximately 806 kilometers per hour, crashed directly into that material. And the worst thing that happened was that there was a scar that was less than 2.5 inches deep. Just to kind of give you an understanding of, yes, it's for radiation protection, but by the time you look at all the reinforced concrete on top of reinforced concrete on top of reinforced steel and concrete, it's also designed to be resistant to collisions. For example, if there is an airplane going overhead or flying over a nuclear power plant, in the event that it crashes into the containment building, which is where we're housing the nuclear reaction, the plane is what's going to be destroyed, not the containment building. And so that's on radiation. And the other thing that conversations that come up is the waste, right? And all energy sources have associated waste. Well, let's talk about this particular nuclear reactor really quickly. A lot of people get surprised when I mention that, you know, the first nuclear reactor, the first known nuclear reactor, is not one that was made by man. In fact, approximately 2 billion years ago in Gabon, Africa, there was a Oklo mine that had conditions that were perfect, essentially, to build to produce nuclear power, right? The primary ingredients, you have to have fissionable atom, right? So there was a concentration of U-235. There were neutrons to initiate the reaction, as well as the groundwater that was able to carry the heat away continuously, right? And the only reason they found this particular mine is that there were some French scientists that were investigating the mine, and they realized that a bunch of U-235 was missing, right? Enough U-235 to make maybe 6 nuclear weapons, let's say. And so the French were concerned that someone had come to this mine, dug up all this uranium, and then were using it to build a nuclear weapon. But after further investigation, and the only reason why they knew that there was material missing is because if you go anywhere on Earth, the U-235 concentration is going to be 0.72%, right? In this particular mine, the U-235 concentration was 0.71%, 717%. I know that doesn't seem like a lot, but spread out over the mine, it was about 200 kilograms of U-235 that just went missing. But upon further investigation, they found that they were never going to find that missing uranium because that missing uranium had been gone for 2 billion years. And that missing uranium was used up through a natural nuclear fission reaction that was occurring at the mine approximately 2 billion years ago. And so when they looked at the conditions that were created for this natural nuclear reactor, the power that was being produced at this reactor was about 100 kilowatts, enough to power 1,000 washing machines for eons. But all of that just went to waste because the energy was not being harnessed. But the idea here is that nature figured out a way to build a nuclear reactor before man did. But also in nature figuring out how to create a nuclear reactor, what did nature do with the waste, right? Is a natural question. And after further investigation, the scientists found that the byproducts or the nuclear waste that was produced as a result of this natural nuclear reactor was underground, and it didn't move more than 10 feet from its point of origin, right? In 2 billion years, it didn't move more than 10 feet. And they discovered this particular natural reactor site, this ancient natural reactor site in 1972. So that kind of gives us an idea of how we can try to look at solving the waste issue or trying to figure out what to do with the waste once it's produced. So in this current day and age, when we take out that fuel bundle, remember when I talked about the nuclear reactor and you have the fuel at the bottom of the reactor pressure vessel, that's basically steel. You take it out of the reactor, right? And when you take it out of the reactor, it's extremely deadly, okay? This stuff is hot. You don't want to really go anywhere near it without any type of protection or safeguards procedure or procedures that implement safeguards, right? Because this material is extremely hot and it's extremely radioactive. So once they take it out of the reactor, what do? They put it in pools, right? And again, the reason why I put it in pools, we want it surrounded by water because it is shielding us from radiation. But not only that, it's also cooling those elements. Because even though fission is no longer happening with these material that has been removed from the core, you're still producing heat through radioactive decay, right? And so the point of putting it in a large body of pool, in a large pool, is one, to shield from radiation, but also two, to be able to cool those spent fuel elements. And after about 5 to 10 years of cooling in that pool, they take them out and they put them in these dry cast storage that's encased in, again, steel, concrete. You see these materials being used over and over again, primarily because of shielding and also physical protection. So they put them in these dry cast storage. And for places like the US, what we've done is we put them in the dry cast storage and we kind of sit them at the site at which they were created, at the power plant sites that they were created, and just leave them there until we figure out from a policy standpoint where we're going to go from there. And that's just specific to the US, just to give you an example. But let's say the US figures out that, okay, well, we're going to bury it in a deep geological repository. Then they take them out of the dry cast storage, they transport them to a permanent geological repository, and then they bury them and leave them there. But is that the only way to do it? Let's talk about recycling for a second. You can recycle 90% of this spent nuclear fuel or this nuclear waste, let's say. So recycle it, throw it back into the reactor, produce more energy, recycle it again, put it back into the reactor about 3 different times. Only 4% of the fuel or the spent fuel that comes out of the reactor really is just waste. You can't reuse it. And so that 4% definitely has to be buried. Okay. So let's talk about this really quickly and how that works. If you look at this graph, it's looking at the radiotoxicity relative to uranium ore, and then it's looking at post-radiation time. If we don't recycle, if we take the fuel out of the reactor, if we take the spent fuel out of the reactor, put it in the pool, put it in the dry cast storage, and then we ended up transporting it and burying it, that material is going to be radioactive for hundreds of thousands of years. If we just took it out and buried it, if we don't recycle it, right? But if we start recycling pieces of it, let's say we recycle uranium and plutonium, right? We are now decreasing the radiotoxicity. So instead of being radiotoxic or radioactive for hundreds of thousands of years, we're now looking at tens of thousands of years. Okay. But if we recycle the uranium, the plutonium, and the minor actinides, right? We can decrease that radiotoxicity all the way down to being radioactive only hundreds of thousands of years. Still sounds like a large number, but at least we can measure it in human timelines that we can plan for and project out for. But that's really the best we can do here. Who's doing this? There are countries around the world that are reprocessing. France is a really good example. France has been recycling nuclear spent fuel for decades, right? In fact, 17% of the electricity that France produces comes from recycling that waste that comes out of the nuclear fuel. And so it's something that can be done. The US currently has a law that says that it's just illegal to reprocess spent nuclear fuel for concern of nuclear proliferation. But if France has been doing it for decades, and that hasn't been an issue, it's leading the United States to reconsider reprocessing of that fuel, because if you have the waste and it can be used, it can be reused to the point where we don't need to mine for a new uranium, and you can reuse it 3 different times, we should be looking at using up our assets efficiently. Again, just coming around to the safety system. People ask me all the time, why is nuclear energy safe? Is it really safe as people say? And it's all in the engineering. That's the simplicity of it, right? So if we start from something as small as the fuel bundles that are in the reactor pressure vessel here, the fuel itself is coated in ceramic, right? And it can reach temperatures of 100 degrees C. And so the function of that ceramic and then ultimately the cladding is to keep the radioactive material encased, right? And that's on a small level. So if you look, this pellet is about the size of a gummy bear, but we're already putting in engineering systems to be able to contain that fuel, contain radioactive material in that fuel. And then we put it in the second barrier where we have the cladding, right, to prevent the release of fission gases. The third barrier is in the primary circuit. And then the fourth barrier is a containment, where I discussed where we have reinforced concrete upon steel and more reinforced concrete, all tucked away and protected in the containment building. And as well as that, the reactors are innately designed, or the power plants are innately designed to withstand natural disasters, right? So here you see earthquakes, floods, tornadoes, storms, aircraft crash, because that's a part of the testing that has to be done before we build out these reactors, and even shock waves. So when we talk about safety, there are a lot of redundant safety systems that are required. It's not an option, required to be built into nuclear power plants. So let's talk about natural disasters for a second. And it's important to me, especially because The whole reason I got into energy is because of energy unreliability, especially during extreme weather events, i.e. time when hurricane season comes around. So let's talk about Turkey Point the Turkey Point, nuclear power plant, commissioned in the 1970s, has an impeccable safety record. Well, back in 1992, right, and this is located in the southeastern Florida, this is probably the closest nuclear power plant to Jamaica. In 1992, Hurricane Andrew, Category 5 hurricane, hit that nuclear power plant head on, right? And the nuclear power plant was fine. Have any of you heard of a Turkey Point disaster? No, right? Because it never happened. But we've heard of Fukushima, right? And just to quickly explain what happened at Fukushima, just to give you some context here. Fukushima, it started with the earthquake, right? And if you go back to the slide here, the power plants are designed to withstand earthquakes, right? So for Fukushima, the earthquake happened. What happened was that immediately the reactor shut down as it was supposed to, right? Because the earthquake triggered a safety event that allowed the reactor to shut down itself as it was designed. But even though the reactor shut down, and what that means is that the fission reaction just stopped, right? So you're no longer producing energy by fission. But recall when I told you that even if you stop the fission reaction, you still have radioactive materials in the core, and you're still producing heat by a radioactive decay. And so you're still producing heat even though the reactor is shut down. And so the earthquake happened, the reactor automatically stopped the fission process. We're still producing heat from the radioactive decay of the elements and the isotopes in the core. What that triggered was the emergency cooling system, right? Because you're producing heat, you still want to bring in water to cool the reactor. The problem was that they put the emergency cooling systems at Fukushima in the basement of the plant. Earthquake, reactor shut down, trigger the emergency cooling systems. Then what came next? The tsunami. As you can imagine, the tsunami flooded the basement that had the emergency cooling systems. The reactor had no way of cooling itself. Hence the hydrogen explosion that happened at Fukushima. But that is, if you look at the historical context, Fukushima is an outlier, and it was a flaw of the nuclear plant, right? By putting the emergency cooling systems in the basement. But let's talk about some other times where you had nuclear reactors that were resilient versus hurricanes. Hurricanes that hit different nuclear reactors all around the globe, and we've never heard of any of these accidents. Same thing for earthquakes. Times around the world where earthquake hit multiple reactors, again, all around the world, Sweden, Finland, India, Czech Republic, Sweden, Japan. I mean, all around the world, we have not heard of any of these accidents. Tsunamis, believe it or not, have hit multiple reactors, again, all over the world, or multiple nuclear power plants all over the world. We have not heard of any of these events because the reactor in the plant was designed explicitly to withstand against these events, and even floods. We heard about the 3 Mile Island accident, right? But there was a flood that happened, and we never heard about the 3 Mile Island flood. So these are just some examples where, reactors versus extreme weather events or weather events, reactors being resilient against these because they're explicitly designed to do so. How am I doing on time, Shalom? Because I could talk all day. I think I have just a few more slides to get to 35. Am I still good?
5 minutes more.
Okay, all right, I'll speed it up. Okay, so a lot of the reactors that are around the world are generation 4 reactors, right? And all the safety systems that I've been talking about are safety systems that are implemented in these really old reactors, right? The ones that are 70+ years old, okay? these are the reactors that we have, but they are already safe based on what we've previously discussed. Even that graphic that we showed where nuclear energy is considered the safest and the cleanest energy source, that ranking of clean is coming from these ancient reactors, right? And so even though they're old, they were built in the 70s and 80s, they're still performing safely, right? Looking more towards a near-term deployment, we're talking about small modular reactors, microreactors, and generation 4 reactors. Let's talk a little bit about those. So small modular reactors are effectively fun-sized versions of the large-scale nuclear power plants, or the conventional ones, right? These reactors can scale from about 50 megawatts, 50 megawatt E, all the way up to 300 megawatt E. And so 300 megawatt E is the largest SMR you can have. And just to give you some context, 300 megawatt E of these small modular reactors is about 1/3 of the size of a conventional nuclear power plant. But you can scale that size down all the way down to 50 megawatts if that's what you really need. What's also interesting about the small modular reactors is that they're called small because they're smaller versions of the conventional ones. It's called modular because you can factory assemble them. They're smaller in components. They require less materials. And then reactor on the name SMR because they're utilizing or they're producing energy by the fission reaction. So just to give you an example of going from what that large power plant looked like, where you have the different components, right, that I showed you through and how it works. The small modular reactors is a condensed version of that kind of uses engineering efficiency to make these reactors smaller. So again, same thing. You have your pressurizer here, and this is for water-cooled reactors, right? Pressurizer to prevent water from boiling. You have the fuel, the core down here. You have the water that goes up through the reactor, through the steam generator. The steam generator is not shown here, but it's connected to a turbine, which is not shown here. And then the turbine to the generator, and then it goes down to a condenser, and then it comes back into the steam generator. But it's all in one module. And this is just a video that's going to demonstrate that much better than I described it real quick.
The new scale power system operation. Control rods retract from the fuel, allowing a fission process inside the fuel rods to produce heat. Water is heated as it passes over the fuel rods, flowing up inside the riser, and then directed down over the steam generators. Heat from the water in the reactor transfers through the steam generator tubes. The reactor water cools and becomes dense. Gravity pulls the cooler water to the bottom of the reactor, where the cycle repeats. Heated water inside the steam generator tubes turns to steam. Steam exits the steam generators, and the pressure carries it to the turbine, where the pressure from the steam turns the blades. A shaft connects the turbine to the generator. The generator turns to make electricity. Steam leaves the turbine and enters the condenser. The steam is cooled and returns to liquid water. Pumps send the water back to the steam generator, where the cycle repeats.
Okay, so that's effectively the water-cooled small modular reactors. But you also have the generation 4 reactors, right? 4 reactor designs. And just ultimately, just because I'm running out of time here, the difference between the small modular reactors and the generation 4 reactors is the coolant, right? So the small modular reactor uses water as a coolant, which is the same water that is used to cool the conventional reactors, right? So the small modular reactors are essentially just small versions of the conventional reactors. The generation 4 reactors, they don't use water to cool to cool the core. Instead, what is used is liquid sodium, right? You can use helium gas in this very high temperature reactor design, and then you can use molten salt in the form of molten chloride or fluoride salts. So really, when you look at different types of reactors, the first question you should ask when you're talking about the differences between them or among them is what type of coolant, what's the coolant that's used in the reactor. If you hear liquid metal, you're talking about sodium. If you hear about a gas-cooled reactor, you're talking about very high temperature. If you're talking about molten salt, fluoride or chloride salt, you're talking about molten salt reactors. Currently, there are 416 reactors across the globe. 59 are actively being constructed. And then you have 200 that have been shut down. But currently, we have 416 reactors. Let's talk about where we are in building out these SMRs. So the first small modular reactor came online in 2019. It's the KLT-40S. But they went a bit further. So they didn't just build an SMR to put on land. They built an SMR to put on a ship that is mobile, that can supply energy to coastal areas. You also have online in China, the HTR-PM and the HTTR-30. So the HTR-PM is a power reactor. The HTTR-30 is a research reactor that's based on the HTR design. And then you have everybody else that's kind of skewed to the right here. Marvel was set for 2024 in this particular graphic, but Marvel has been pushed out to 2027, ultimately because of the concern for the availability of high assay low enriched uranium fuel. So the fuel that you're going to be using to power these small modular reactors. Ultimately, it's a challenge because a lot of that fuel was expected to be sourced from Russia, but with the geopolitical challenges, a lot of different countries around the world are kind of coming up with their own solutions, and that's taken a little bit of time to develop. But however, the United States, we started producing our own HALEU fuel last year, and so we're well on our way to being able to produce HALEU for or future fleet. I'll skip this. This is just all around the world. We have different types of SMRs that are being developed. That just goes to show that there's a lot of interest in SMRs. And then for a lot of the work that I'm doing when I go to Jamaica, right, again, is developing these technical programs to introduce nuclear engineering as a field. So we're talking about highly technical concepts, whether I break it down for high school students, university students, or for the general public. I think it's important to address that social issue of understanding what the technology is, understanding the field, understanding its history, its present status, and its future, so that we can have more informed discussions on the potential deployment of nuclear energy. This is a video you can find on YouTube. Check it out. This is a film from one of the engineering boot camps I did in Jamaica. I'm ultimately looking to exploring doing the same programs in developing countries all over the world. This is a part of the international initiatives that I host. So if that's something that you're interested in, you can get my contact information from Shalom. And I will wrap it up there.
I say, oh, yes, wow. That was amazing. That was really amazing. I didn't want to stop you at all. I was just saying, I wish we could have another section where nuclear energy, like,
Yeah, I definitely
yeah.
have more slides in the back.
Mhm.
I knew I would be over time.
Okay, we'll have to do something about that so that in case people are more interested in learning, because I know people, here we have like a mix of all the energy systems. So people are interested in solar, some are interested in wind, some are interested in the marine and all of that. So maybe we can collect more responses from the audience, and if a lot are requesting for the nuclear material, like more nuclear knowledge, we can just try to see if we can set something up. And
Yeah,
I'll reach out to you again.
absolutely.
Thank you so much.
Definitely. I can't see the questions without having to touch here. So somebody could let me
Yeah.
know what they are.
Yeah, there's one question, and then I had one kind of inquiry. So
Yeah.
the question that I have here is about the waste. So you talked about the waste for nuclear. So the question is, what are the waste for solar energy?
So the waste for solar energy are really the panels. And so when you talk about the front end of all the different energy sources, and the critical minerals that are needed to harness certain energy sources, we're talking about for solar and wind, specifically more on the solar end, but also wind. What you're looking at are the panels, because right now a lot of the solar panels or the solar plants, at least in California, that we've seen that are coming close to the end of their lifetime, they're working on trying to come up with recycling processes to recycle solar, but as of now, what California is doing is kind of dumping them into a landfill. Same thing with the wind turbines. And so that's currently the plan, or that's what is actively being done, but that doesn't mean that they're not looking at ways to recycle this material. One of the reasons why it's kind of difficult for wind and solar is that on the front end, where you mine for these critical minerals, these rare earth metals that you really need to be able to create these panels and create these wind blades, you can kind of think of those as, if you have a dough, right? And the dough you're gonna use to, I don't know, fry dumplings, or you're gonna use the dough to, I don't know, do something with it, right? You have your flour, you have your salt, you have, let's say, maybe a baking powder. You can consider that as your panel, for example, right? And when you talk about recycling, what we really want to be able to, if possible, extract are the rare earth metals, right? So we don't have to keep on going and mining for those. The salt in that dough represents those rare earth metals. And so if you can consider you used a bunch of flour and baking soda and just an eggs, and you just a tablespoon or just a little sprinkle of salt, what's really valuable for recycling is being able to access the salt. And so it is a challenge, but there are different research activities that are ongoing to figure out how we can effectively reuse this material, because mining for rare earth metals currently is a huge issue. And China really holds like more than 80% of the rare earth metals production in the world. And so that's something that is being investigated. So not to say that that's something that we can't do for solar, but when we're talking about the waste, we're talking about literally taking the panels and the blades, and right now, at least for California, dumping them into a landmine.
Oh, wow.
Landfill, not landmine. Oops,
Okay.
sorry, landfill.
Wow, that's really not sustainable, but let's see how far the research is going to go. I think there was this
Yeah.
question, Pamelaxi, at the beginning when you mentioned that nuclear plants are the safest, and you were comparing the distances to nuclear power plants. So the question here is, when you talk about the distance, what distance is considered? You
So
said
for the particular graphic that I showed, that was living about a mile from a nuclear power plant. Yeah.
Yeah.
If you live about a mile from a nuclear power plant, you're receiving less dose, 1,000 times less dose than if you were to go to the doctor to get a CT scan.
That's impressive.
Yeah.
Wow.
And yeah, it's interesting because I mean the nuclear industry is something that where radiation is, I mean, we knew from the jump that radiation is something that is a byproduct of the industry. And so safeguards, essentially you use engineering, you use technology, you use science to be able to make dangerous things safe. And that's what we've done. And when you talk about planes, really, if you take a plane across the country, you're flying in this a thin in a thin material. I mean, how many feet? I don't know, 5,000, 50,000 feet in the air, 20,000, 50,000 feet in the air, over thousands of miles, and you feel safe doing it, right? It is because of all the engineering and all the work that the safeguards that goes into making sure that it is safe to do so.
Yeah, I love that. That really resonates with me. Science really makes dangerous things feel safe. Yeah. Oh, so thank you. Thank you so much. I don't know if there are any more questions for our speakers, and I think that will be all for this part of the presentation. Although we have like a youth discussion hub where we invited people from like youth from different sectors. So if you are having other engagements, it's fine if you want to drop off now. And this section is more like an interaction section for all of the audience and the participants. So it's fine if you stay, but if you wish to if you wish to go, it's also okay. And to open that discussion, we do have a guest here, Mr. Aldi. He's going to start with geothermal energy, and then we continue the discussions around wind and also geothermal energy. Mr. Aldi, are you still here? Oh, okay.
Hello, can you hear me, please?
Yes, I can hear you.
Okay. Hello, everyone. Good evening, actually, from Jakarta.
Thank you so much for joining. Do I share my screen for you, or would you share your screen from there?
I will share by myself. Okay. Okay, can you see my screen?
Oh, yes.
Okay. I think the participant mostly from Nigeria, right?
Yeah, we have a mixed audience though, but more of the population are from Nigeria.
Oh, yeah, I have a lot of friends from Nigeria, from Abuja, Lagos, Katsina, and even I know one language. Yakake.
Let's be honest.
Okay. Okay, thank you, Salam, for inviting me for this discussion. Hello, everyone. My name is Aldi Cahya Muhammad. I did my bachelor and my master in electrical and electronic engineering at Islamic University of Technology, Dhaka, Bangladesh. And right now, I'm a doctoral student at University of Indonesia in the same major. And also, my current job is as a business development manager at a Radian Group, one of the biggest energy services in Indonesia. And also, as a practitioner, I have done several projects development related to energy transition and net zero emission. In these 10 minutes, it's privilege to join you today to discuss one of the most promising and sustainable energy sources that our planet offers. If there is a question or future collaboration, please you guys can send email to I will send you the email to the chat after this presentation, because due to the time zone and I have another schedule, so maybe I can maybe only present this presentation for the discussion or sharing session. Maybe you can send me through the email and I will answer through that. Okay. And then okay, and next it okay, for geothermal energy is derived from the earth natural heat, present a unique opportunity to meet our growing energy demand while minimizing environmental impacts. As the world continues to seek cleaner and more efficient energy solutions, geothermal energy stands out for its reliability, sustainability, and potential for reducing our carbon footprint. And also the component of the geothermal energy system, one is the geothermal reservoir, to its wells, which is there is a production well and injection well, and also the surface equipment. For the geothermal categorization, there is single flash, which is used for electricity conversion when the geothermal production well are production in mixture of brand, and also double flash. That the steam power plants are proven of the single flash, which is, and dry steam power plant are often used in the most efficient power plant with high enthalpy for dominant, and which is it is more higher temperature than the single flash, and also the binary power plants and also hybrid power plants. And also for the single flash system, this diagram shows the design and the installation process of a single flash geothermal energy system. First is the J well or production well. The hot water or steam is extracted from deep underground reservoir through a production well and goes to the separator or the flash tank. As the extracted fluid is sent to the separator where steam is separated from the liquid. The steam is directed to a turbine, while the remaining liquid is either injected back into the reservoir or used for further energy extraction. And then goes to the turbine. The high pressure steam drives a turbine connected to a generator. The steam passes through the turbine. It causes the turbine blades to spin and generate the electricity. And also the
we can only
yes.
see your slide. We do not see the slide you're presenting currently.
Oh, it's not moving.
Yeah, it's not moving. Okay.
I think when I full screen, it's moving, right? It's moving right now.
We still see only the first slide. Maybe you can just go to the slide of the geothermal energy illustration. That would be okay. Yeah.
What about like this? You can see the full version, right?
Yeah, I can see. We can see the
Okay.
demonstration.
Okay, then I just talk about this one. And the generator, the turbine, is connected to a generator that convert the mechanical energy from the turbine into electrical energy, which is then supplied to the grid or used locally. Then goes to the injection well, and then piping valves and others. And these steps illustrate how a single flash geothermal power plant operates, converting geothermal energy into electrical energy through the use of steam turbines and associated components. This system is commonly used in areas with high temperature geothermal resources. And also, this one, the enthalpy and entropy diagram. I think it's more complicated because I will explain you in the simple way that the diagram typically shows the boundary between different phases in the working fluid. For example, the water or the steam. The saturation lines, this line represent the condition under which the fluid is in a saturated state. Means it's about to change the pace. And also the saturation liquid line, the line where the fluid is about to start vaporizing. And saturated vapor line is the line where the fluid is about to start condensing. And also the process path. The path is a fluid takes during a thermodynamic process can be plotted in this diagram that's showing that the change of an entropy. For the point 1, for example, the state of the geothermal fluid at the production well, and the point 2 is the state after being separated, where the steam is extracted for power generation, and also the state 2 and 3 is the state of the steam after expanding through the turbine. Point 4, the state of the steam after it has been condensed back into water in the condenser. And it allows the where the energy losses occur, particularly in the turbine and the condenser. By analyzing this diagram, the engineers can optimize the process parameter to improve energy extraction and reduce losses. And also there is pros and cons of geothermal energy. The pros is renewable and of course is sustainable and low emission, base load power supply, high efficiency, small land footprint, direct use application, economic benefit, and also energy independence. And also there is a cons. For one of them, geographical limitation, high initial cost, resource depletion risk, environmental concern, water usage, complex site development, and for example, like noises also during in the geothermal power plant. And this one, the case study of Indonesia, which is Indonesia is the largest archipelago country in the world, and we have more than 127 volcanoes and more than 342 potential geothermal wells, which makes Indonesia is the second largest producer of geothermal energy. It is because Indonesia located in the Ring of Fire. We are surrounded by three plates: Eurasian plates, Pacific plate, and Indian Australian plates. But the issue of the country in the Ring of Fire region is too much earthquakes. Indonesia, Philippines, Japan's. Yeah, they are the country that almost every day there is earthquakes. That's the another issue during the Ring of Fire region. But because of that region, we have the unlimited energy, which is geothermal energy, and this is geothermal. Is different like another energy. We cannot move the energy by sudden like that. It is gifted in the country that they have these resources. And directly for the future potential, this is that I show you the map of geothermal development, because I'm here as a business development. There are future development in Indonesia. Still, there is there are stages for the geothermal. First is the exploration stages, and second the exploitation stages, construction and production stages. As I told you before, that we have more than 342 wells, which is one well actually more than or maybe geothermal in total in Indonesia is more than 230 gigawatt in total, but still only few of the potential that Indonesia can implement it. And this is the data from the PLN. PLN is Indonesia's state-owned electricity company that is heavily involved in the development of geothermal energy projects across the country. And for example, the geothermal development map of review in Sumatra, this cursor is Sumatra. There are Sarula geothermal plant is located in Sumatra, and this one is one of the largest geothermal power plant in the world. And so Muara Laboh, another significant geothermal project contributing to the grid. For the Java Island, it is a Java Island, and there is a Patuha that located in West Java. And then Dieng geothermal power plant is located in Central Java. Wayang Windu also in the West Java. Karaha is still also in the West Java. Ulu Belu in Lampung, and also the Lahendong. For example, in the Wayang Windu, one geothermal power plant, the total capacity is 330 megawatt, which is this is the largest single contract geothermal power project in the world. Okay, and then the second is For the Wayang window also do 227 megawatt. That is known for its high efficiency and significant contribution to the Java Island electricity. And also Ulu Bulu is 224 megawatt. And also in the Sulawesi and also the Lahendong. Okay. And then for this future potential, actually, there are some issues that I have been studied before. That one of the cons that is very high in the initial stages or initial investment.
Hello, Mr. Adi. We seem
Yeah.
to be running out of time.
Okay. Yeah.
Yeah.
Okay. So I think okay, there's what I will discuss another issue that the machine learning. Okay, because why we don't maximize this potential, because we don't use the technology. For example, those the get of artificial intelligence in this case is the machine learning. And then okay, I think machine learning is the key for the Indonesia or the rest of the, if you want to maximize their potential. Okay, and then this is actually my model that I want to share to you guys, that in 2019 I have an award from the Geothermal Association, and this is the model. And also why the machine learning, and you can read this one, because maybe the time is limited. Okay,
Yeah.
so if there is question of future collaboration, maybe you guys can send through the email, or Salom, you can help me to no, I will put it here on the channel.
Yeah.
You can
Thank you so much.
share.
Thank you so much.
Yeah.
Thank you so much, Mr. Aldi. Your model and everything, I greatly appreciate it when I see efforts towards like scientists bringing up their own innovations, bringing up their own work, and also trying to solve the energy problem. That's really impressive. And to round up the section, we wanted a moment for all participants to quickly, and that's why we started with Mr. Aldi, to share a little bit about what they do in the energy sector and how can we collaborate between ourselves. Also how to know, how to identify opportunities, resources, and like the knowledge we need to gain to be able to strengthen our ideas around the energy sector. So this moment, we could all turn our cameras on if we have the privilege to do so. Like if you're in a good environment, it would be so great to see faces. You can unmute yourself, a little introduction about yourself. I'm seeing already amazing people that I know, and it will be very great for us to just discuss a bit before we round up the section. So while I wait for someone to indicate that they're going to speak after myself, I'll go ahead to say what my background in energy is, and if there are questions for me as well, you could go ahead to share them. And I hope it's going to be interactive. Okay, so once again, I'll just introduce myself again. I'm Iba Shalom. I'm doing my PhD in chemical engineering. Basically working on the multi-objective optimization of tailor-made biofuels. So we deal a lot with designing biofuel pathways and looking at solving mathematical models that will give us the optimal technological route. So not so similar to what Mr. Aldi is doing. He's deploying his own mathematical model into geothermal systems. For myself, I develop a lot of mathematical models, but towards biofuel optimization. And right now, I think there are like a lot of potentials around like lignocellulosic biomass. However, those biorefineries using such kind of waste materials haven't fully been developed. So a lot of research is ongoing around this area. And I'm just looking forward to maybe any resources or someone that is interested to learn about it. We can discuss, we can share ideas. And yeah, that's from my side. So any other person that wants to go ahead, you can just raise your hand and take the floor. Florence, if you're trying to speak, I think you're muted. We can't hear you.
No, sorry, I'm just joining again. Sorry about it.
All right. Ms. Joy, do you want to say something about what you do? I know you're doing incredible work. So, I mean, it will be great if you can give us the pleasure to hear from you.
I knew you were going to call me, and I was hiding. I was already typing. I knew you were going to call me. I said, oh,
Sorry.
God.
Sorry.
Hello, everyone.
That's me.
Yeah, hello, everyone. My name is Joy. I really learned a lot from this first speaker and the second speaker as well. So we're not able to hear you completely clear, but I know I grasped a lot, some few things. And thank you so much for your innovation. You know, I love anything innovation. I just love it. So my name is Joy from Lagos, Nigeria. I am the founder of Zama Solutions. At Zama Solution, our core focus is solar energy. So that was what I was asking regarding solar energy. So apart from deployment and installation, one of the things we do is capacity building. For now, we don't have any innovation, but we hope that in the future, when we enable youth, when we equip them, they are able to now, come around and then innovate solutions that solve energy poverty in Nigeria and worldwide. So that's just basically what I do.
Okay. Any other person working in solar that wants to speak? And Charlene, if you have something for anybody, or Meloxy, if you have something for anybody, please feel free to jump in. Cynthia, I see your video already. You could go ahead. Cynthia is working with us at Renew Words too, so it's been amazing having everyone together join the call.
Hey, hopefully everyone is feeling okay. So what I can just say is a big thank you to the speakers. Although I joined late, I joined when Charlene was presenting, and it's really interesting. I never knew all this stuff about nuclear energy, and I'm like, oh my God, okay, this one could be really explored, especially in the African continent. I don't know if it's being explored currently. And then the session about the geothermal, but in Kenya we use a lot of geothermal, and it was really interesting, and I hope the speaker will bring his innovation to Kenya. It will really help, especially the ML model was interesting to me. So yeah, keep it up. And thank you all for giving us this important knowledge. Yeah.
Yeah, just following on that, Cynthia, there is one nuclear power plant in Africa, but it's in South Africa, Cape Town. It is about 40 years old now, and it produces just under 2 gigawatts of electricity. So there is an infrastructure for nuclear energy specifically in South Africa. I know Ghana has been looking at long-term deployment plans. Morocco has expressed interest to look at nuclear. So is Nigeria. Nigeria is also on the list. Tunisia and some others. But for now, Egypt is the only country that is in the process of constructing a nuclear power plant. But South Africa has had a nuclear power plant operating safely for decades already.
Oh, that is quite interesting to know. And given I'll be in South Africa next month, I will try to see
Cape
if I can
Town,
get
check them
more
out.
information.
It's
Okay.
they call it Coburg
Oh,
nuclear power
okay.
plant. Yeah,
Wow.
Koeberg.
Okay.
Wow. And I'll just throw out a question, and this is for everyone to answer. So with the energy transition, do you think it's a one energy stuff, or is it about the mix? What do we think about that?
It's definitely a mix. There's no, I don't, you can't apply that logic, I think, across the board. So for example, I know I talk about nuclear energy in the specific context of Jamaica. Solar, I definitely think the government should lead with solar. Because I mean, we have a huge capacity for solar, but at the same time, because more than 80% of our firm electricity comes from oil that's imported, replacing that, trying to bump up solar so that so that it covers a large portion of that, but also having a diverse energy mix of other firm clean energy sources to kind of chip in, like as batteries, for example, for the smaller micro reactors, I think is a good option for Jamaica. But for places like St. Vincent and the Grenadines, St. Lucia, that have immense untapped geothermal power as a firm baseload reliable potential, they have no business looking at nuclear energy technology. They should really focus their finance and their energy on building out that untapped geothermal. And so it really depends on what assets you have, regionally speaking. And then looking at, okay, well, if you have access or have a high capacity for one of the firm, reliable energy sources that is also clean, consider that, but also consider the profile of other assets that you can take advantage of, whether it's wind or solar or, well, hydro and geothermal could be considered in the firm category, but you kind of tailor it based on what your region's assets and needs are.
Yeah, that's quite insightful. I think Esther is raising her hand. So your name, the renewable energy project you're doing or something like that, then you could share what you want to share with us.
Okay, I don't know if you can hear me. Good day, everyone. My name is Esther Uzuroha. I am speaking from Lagos, Nigeria. I just want to ask a very simple question to Charlene Smith. Okay, I don't know my background. I am a core member in Nigeria. I'm actually serving my country for 1 year, and I'm doing my service in a refinery that uses turbine, and that brings me to my question. So the refinery I work with, they use turbine, they use steam turbine to generate electricity. And one thing that's really been disturbing is that this turbine makes so much noise. Like, it is very noisy. You can barely hear yourself there. So I wanted to ask Charlene Smith, you mentioned that for the nuclear energy, the whole module has like a turbine embedded in it that does the whole energy conversion and all of those things. I just want to know, I've not seen a nuclear energy plant before, I've not been there, but I want to know, does it make so much noise? Like, how is the, like, if residents around there, like, does it make so much noise? I mean, the whole module. Yeah, thank you.
Yeah, thanks for your question, Esther. Yeah, I mean, it's not a silent. I mean, it's the blades are turning, so you're gonna expect some noise there. But what's I think unique about nuclear power plants is that you don't have residents in the immediate vicinity. And so a lot of the noise that is produced by the turbines, it's confined to the site. And so you wouldn't be at your house hearing the turbines spinning, for example. For your smaller for the small modular reactors and the microreactors, for example, you're looking at much smaller systems. You're not producing as much heat. You're not utilizing as much water, and so the noise ratio is significantly reduced. But and at the same time, there is a 5-mile distance, I believe, in general. It varies, depends on whether you're talking about different microreactor designs versus small modular reactors, but the noise component is not something that is concerned specifically to residents in the area. Maybe the workers complain, but after working at a power plant for, I don't know, the lifetime of it, which is at least 40 years, right now they've extended up to 80 years, the lifetime. I mean, it's not one of the issues that are foremost in our minds, because I mean, the complaints around that, specifically from residents, are just not there for nuclear specifically.
Okay,
Okay,
I
thank you
see
so
another
much.
hand up. Although there's a question that will call for a little bit of interaction between the audience. I think Gesham, you can just your name and if it is a question or a contribution, anyone.
Okay, good everyone. You can hear me now?
Yeah, it's breaking a
Hello.
bit, but yeah, we can hear you now. The, no, we can hear you clearly. I think that you have to send your message in the chat. We can hear you. Yeah, thank you so much, Charlie. Thank you so much for joining the section. Thank you so much. I do understand and it's okay. Thank you. Thank you.
Ciao.
Yeah. Right. Gershom, I think you have to check your internet connection and try to connect again. I think the only question that I would love maybe Melaxi to speak on, and if you if you also want to run, it's very fine. So this question is from the Miss Joy. She said that Africa is the richest in like solar and resources in the world, but it has just installed only 5 gigawatt solar PV. And what could be the cause? You know, you work a little bit with Africa. Is there a major reason why Africa doesn't seem to harness the resources? And, you know, how can we also help Africa to be able to utilize the resources better?
That is an excellent question, and I do not have an answer for it. I can tell you how the resources affect my ability to go into Africa. The biggest thing is, again, resource availability. Can we get our materials out there? Can we get the research done in the region, and things like that? So it might have a lot to do with the ability to be able to get the resources out to the location. So otherwise I do not know the answer for that one.
Oh, thank you so much. Thank you so much. I really appreciate your time. I know you said you have just from 9 to 11 framework. So if that is still the case, it's okay to, you know, take a rest, because I know it's a lot to speak to us for so long.
I can stay on. And then I was also going to mention, I went over river energy today. If anyone has questions about tidal energy, I'm happy to answer those if they want to email me. There's so many resources for that, and I'm always happy to share the information between the two different technologies.
And to follow up on that, what's really the difference between river energy, wave energy, tidal energy? Sometimes it seems confusing whenever it's being used.
All right, so a river device is meant for rivers. Tidal devices are on the shore. So they'll be in deltas, in bays, things like that. We have projects in Cobscook Bay. We have a project in Cook Inlet in Alaska. So you have the Bay of Fundy, which is a very popular tidal resource. So that is where we see a lot of tidal devices, is along the shore. Wave devices can go a little further out than tidal devices can, and they really should, because of the resource availability out there. Like, there are more waves further away from shore than there are inshore, or at least larger when you have the availability. So those are the different locations. And steadily, I can say that the most steady steady electricity producer will be river, followed
Okay.
by tidal, followed by waves.
Okay, and then when it comes to river energy, I was like, I know you said it could be installed like in shallow places and even 5 to 10 meter deep. And
Mhm.
I was just wondering, can people construct like their own reservoirs and still install your system, the product in them? Or must they have to be a flowing river all of the time?
So we actually, in one location in Canada, we work below a dam. So we work with the dam. Let me remember the name of the type of oh goodness, give me a second to think.
Okay.
I need to remember the name of it. Oh, the pumped power, the pumped storage hydropower. We work with them to be able to move the water from the lower reservoir to the upper reservoir. So they require power for that. They could use battery storage, they could use anything else, but they are using our device below the dam. And whenever they open the dam, we're able to produce the power that way and then get their stuff back up to them. I can give a link that explains how that sort of dam works, because that might be more helpful in understanding our role in that process.
Yeah, definitely. That would be really helpful because I think it's something that I would love to know. Just to be able to hold conversations around tidal energy. Yeah.
Yep.
Thank you so much.
No problem. Again, like as we were mentioning earlier, I think all of the different types of power need to work together to be able to be successful.
Do you have, aside the fact that you're working in tidal energy, do you have any preferences for other sources of energy?
I love nuclear energy, so so this was a great topic for me today.
Oh wow, that was such a great coincidence.
Yeah, it was.
Oh, and okay, thank you so much. I'll throw back this question to the rest of the participants. So still going back to Africa, because a lot of us seem to be from Africa. But if you are not from Africa, you're going to tell us what source of energy is like the best for your location. I know Dr. Chalin said something about like leveraging the resources that are currently in our location. So the question is like this: which energy solution, in your opinion, is the most people-friendly in terms of cost and health benefits? And while answering this question, you tell us where you're from and then go ahead to answer the question. Like depending on your region, which of the energy solution is most people-friendly, and health-wise, what do you think are the benefits? Anyone could go ahead so I don't put people on the spot.
I can go. I can
Okay.
go. Yeah,
Okay.
yeah. So I'm finding the thing about Tidal interesting. Okay, but yeah, I will watch the recording later. And then in Kenya we have a mix. Basically, in the urban places we get our electricity from the plant, the geothermal plant, and the hydro plant. And then in rural areas it's mostly solar, like because most of them are off grid. But also the people who are on the grid, they use the mix that is available, the geo and the hydro. So yeah, that's what I can say about Kenya.
Oh, that's nice. I also, okay. Florence, you want to say something?
Yeah, I want to say something. So I'm from Florence. I'm from Sierra Leone, West Africa to be precise. So for Sierra Leone, basically we are using, for the renewable energy, we are relying on two types, the hydro and the solar. And basically you do know that it's seasonal. We have the rain season in Sierra Leone and the dry season. So because of that, during the dry season, the climate issues, we do have problem with the dam because the hydro dam produce less than its capacity during the dry season. So we tend to rely more on the sun during the dry season. So we are using a mix of both, but we are using more of the solar because of the grid system. So we are using more of the solar for the remote villages and so on and so forth. But we are using a mix of both. Just for now in Sierra Leone, we are just using the solar and the hydro. We don't have the geo, the tidal. I've heard about it, but it's a bit new, and I'm happy to hear that other country are actually exploring it. And also, there's a bit of discussion around the nuclear, but you do know the myth, so I was really happy hearing about it today. But there is still a lot of misconception around this nuclear energy. So yeah, but I do add about it that even we do not even have a radiotherapy center in Sierra Leone. They have talked about it I think about 3 or 4 years ago. They are still on the planning stage to build a hospital that will use radiotherapy as a treatment center. We do not even have that kind of facility. That's the fear of nuclear power in the country. So they're still on that phase. And recently, I think this week, we did launch the gas power plant, just this week. Yeah, so we'll be talking about gas power now in Sierra Leone. They did launch it this week, yeah. So basically, but it's just these two that we have been using for now, apart from the thermal that we are trying to move from. But they did launch the gas power plant this week. I don't know much about it yet, but they did launch it this week. Yeah. So that's Sierra Leone for you.
So if you, I don't know if when the time you joined in, but you know, the nuclear section had a lot to say about the misconceptions, the disasters. She addressed that, and also told us the reason why, you know, the Fukushima the nuclear disaster.
Yeah, I was actually lucky to repeat that part. And I read physics, so doing my internship after university. I was placed at the Nuclear Safety and Radiation Protection Authority. That basically their function is to monitor any industries or hospitals that are using this radiotherapy radioactive materials. So basically, I think that's one, as I said, that is the same major issue we do have opting the radiotherapy hospital for cancer treatment and so forth. I did my internship with that office, I think about 6 years ago, and they were talking about that plan. Up till now, it has not yet.
Oh, that's one problem with Africa.
Yeah, that's one problem. And I think it's still around the misconception and fear of this nuclear devices. So basically, maybe they are thinking, so what are the modalities do we need to put in place? You know, this radiation, it's something that is harmful. It's this, is that. So I'm guessing maybe that's one of the stumbling block in terms of erecting that hospital. So it's about 6 years now since I left that office, and up till now, it has not yet materialized. So yeah, I do understand the fear. I do understand the conception. Even when I was doing my internship there, I had some colleagues. Florence, I hope you and that your radiation office that you are working, you know, you have to give birth, eh? You know that this radiation it causes cancer. It does this, it does that. I'm not even dealing with the materials directly. I'm just at the office learning and everything, and they still have that fear. So I can't imagine what it means to actually deal directly with the nuclear materials. So yeah, I do understand the misconception that she was talking about. Yeah.
Yeah. I think they will have to listen to this presentation so that they can change their mind. If they listen to our webinar and the great potential
that's why I said
from
they
nuclear,
need to do
that will
more
change their mind, definitely.
on this nuclear.
Yeah. That would change their mind. And going on that, I like anyone could jump on the call to speak. But I saw that Lenoxy sent in some links about like the process of electricity production, how the flows happen from lower reservoirs to the upper one, right? I think that's the link that was shared in the box, right? For those that want to learn more.
Yeah, if you want to learn more about how we're involved with the dams, because that question came up, that is one of the ways we work with the dams in power production. And of course, when they open the dam, that's when we power, and then we go to a battery storage to work while the water's not running. Yeah.
Okay. And thank you so much. Oh, David, yeah, please.
Yeah, thank you so much, Melissa, for that informative session. Very powerful. And Dr. Smith also, you know, since after the Hiroshima Nagasaki incident, I had this very strong distaste for nuclear, anything nuclear, and I'm like, whoa, no. Yeah, so but really today really cleared up a lot of doubts, brought in a new perspective for me, and I'm like, oh, I think I should consider this nuclear energy thing right now. So currently, I'm in Florida right now. So here in Florida, I would say it's called a sunshine state. So a lot of sun. I would say the most friendly energy source would be solar. Yeah, from Nigeria. I'm from Benue State. Yeah, if you know, yeah, it's has a river around. So hydro, I would say. So here, solar, because of course, the sun is something else. You should come to Florida someday. Yeah, so that's all I have to say. Kudos to you, Shalom, for putting this together and the team, and hope for greater heights.
Oh, thank you so much. I don't know, Naloxi, do you have any offices in Florida?
So funny enough, our founders actually came up with the concept of ORPC while they were in Florida.
Ooh.
So back in 2004, on the back of a napkin, came up with the concept for ORPC. Unfortunately, we don't have anything in Florida right now because the flow of the tides is not strong enough.
Okay.
Yep.
Oh, I mean, yeah, it's the sun definitely that is up always. Yeah. I think I would have to call maybe Jessica. Jessica, can you share with us, or are you not in a comfortable place? Jessica or Anita, yeah, we haven't heard from you during the section, so maybe 1 or 2 words and then we end the section. And Jonathan, of course. Any of you can start. And the question again was, what is the energy source that is most friendly to your location? And what do you think also are the health benefits of that particular energy source?
Good afternoon, good evening, everyone. My name is Jonathan. Can you guys hear me?
Yeah.
Okay. My name is Jonathan, and I'm talking or speaking all the way from Nigeria, Port Harcourt to be precise. Over here in Port Harcourt, I would say, due to the fact we have natural, how would I put it, the presence of oil is an oil-rich state actually. So, like where I'm located, we make use of what they call the gas turbine that generates electricity, right? So, from how am I going to put it? Well, we have generators that use gas to generate electricity. Gas turbines in actually generate electricity here in River State, Port Harcourt. We don't really have much of the wind. I haven't really seen anyone in Nigeria. I'm from Kogi State, basically, more like the confluence state. And one of the neighboring states, I think Niger State has a dam, the Kainji Dam, that generates electricity as well. But over here, some parts of like River State, we have a gas turbine that generates electricity for us. So more like most persons are actually going into the renewable source of energy like the solar, although we don't really have it as much as the sun is not so much, it's not as hot as it is as compared to our friends who are actually in the northern side of Nigeria, like the northern side of Nigeria. So that's it. And I would say I was actually exposed to a different light when it comes to the nuclear energy and the tidal energy. Yeah, we learn every day, but this one really exposed me to a whole lot. And I'm really grateful to Melosi. Thank you so much. Uh, when I saw the reef gen, right, it looks more like a submarine, a mini submarine, but then it's good, it's cool, and I think it's really it can be obtainable in most parts of Nigeria, like the riverine areas, most side of River State, like the Bonny Island and all of that, and perhaps the coastal regions too, Bayelsa, Lagos, I think, yeah, Ogun State, some part of Ogun State, yeah. Then the nuclear energy, I don't think Nigeria doesn't really have much of more like nuclear energy or reactors. We've not really had anything regarding that. But then I've been exposed to seeing that the nuclear energy is one of like the safest, which is kind of surprising. I think there was a lady, I think it's Miss Joy, who just screamed wow when she joined in, and she kind of got that information.
I was shocked. I was very shocked.
Yeah, because I think I think it has to do with information, right? And the way we've been informed about nuclear energy and the rest. And I think my exposure when it comes to most of these Hollywood movies that has to do with getting nuclear goes stuff um, uh, for nuclear weapons and all of that. So saying or hearing that is kind of safe to me, it was mind blowing. And I would say it's really it's educative and informative as well. So shout out to Challenge, shout out to Melozi. I'm grateful for that for these lectures, and I hope to have further interactions and lessons and webinars to gain more insights when it comes to this. So thank you so much.
Yeah, thank you. Thank you so much, Meloxi. Thank you so much. It's such a pleasure to have people talk about these rare technologies, and it's fresh knowledge because we are basically exposed to other sources of energy. So if you could listen to our conversations, you hear people saying a lot about having solar in their home country or wind. How many of us mentioned Tidal? Maybe, maybe none. Maybe none. So it's something that it's a new knowledge, and I'm so grateful that you joined the conversation. And I think we would end here. I don't know if Jessica still wants to say something, but if she's not saying anything, we might have to end here. And I just want to say thank you to everyone that stayed till the end. Thank you so much, Meloxi. I'm so grateful that you joined us. Thank you so much for your time.
Thank you so much for having me.
Thank you so much. And thank you so much to the ORPC team. Great shout out to them. And I'm wishing you all the best and hoping to see more of your the projects that you're talking about to Nigeria. And possibly please let me know when the projects are going on. So
yeah.
Yeah,
I can do that.
So much. Yeah. Oh, I'll look out for that for sure. And thank you so much, Cynthia. Thank you, Florence. Thank you, Mrs. Joy. Thank you, Jonathan. Thank you, Jessica. Thank you, Esther. Thank you all so much for staying to the end. And we'll end our section here. And have a great weekend, even though we spent a lot of the weekend with you. Thank you so much. See you in our next edition. Thank you.
Bye. Thank you so much. Bye. Thank you.
Thank you.